All right. So how many of you know what that movie clips was from? Which one? Which movie is that? Inside Out. Okay, I don't know if you have a top list or favorite list of Pixar movies, but for me, it's definitely Inside Out. Is on a on a top two. The other one that I'm debating with Inside Out is basically Soul. I don't know how many of you watch that one as well. Yeah, so this two they are both on my top list. Well, there is Inside Out too, but I'm sure that Inside Out 2 is not on my top two. But part of the reason that I particularly like Inside Out is not just because I was crying when I was watching it. It's also because when I watch that movie, I'm coherent with one of my main topics in my research. That is memory hierarchy. However, if you don't have the chance of watching the very first version of Inside Out, you probably don't know why am I talking this. So sometimes we need to do some commercial, even though like we are listed as free YouTube channel, right? So give them some copyright. So if you want to remind yourself what's Inside Out about, you can still find it on, I guess, Disney Plus. And recently, I think you can also find Inside Out 2 on Disney Plus. But before we start, let's talk about, let's put everybody on the same page again. So we were talking about that all the machines that we are using, basically they are von Neumann architectures. And the basic idea of von Neumann architecture is that whenever you have a program, we compile it into a list of instructions and a collection of data. When we want to run these programs, it must be the case that we have to load all the instructions and data that we need to execute the program into the memory before we can run them. And whenever your processor wants to execute a program, it is essential for each instruction, we have to process them in a way. First of all, the program counter, which is a register in a processor, would indicate where in the memory should I get that instruction. And then I would start executing this instruction by very first, I have to fetch this instruction from the memory to the processor itself. And then the processor will look into the fetch content, and then we can finally decide what kind of ALU operations we need to perform accordingly. And then in case your ALU operation, or we identified that this is a memory operation, we need to access memory, then we will trigger data access request to the memory. And then finally, we advance the program counter and start fetching another instruction, start executing. And the beauty of this von Neumann architecture, as we said, is because we love it because we don't have to change any of the hardware configuration, and your computer can automatically have different features. And the last time we talked about MDOS flow. And one of the most important takeaway from MDOS flow is probably we want to make the most common case fast. But other than that, we also have a lot of other things that we have learned. For example, each optimization have an upper bound, and optimization is basically a moving target. Like after you optimize something, some other problem becomes another new major problem. Or another thing that you have to recognize is that we are living in a world of parallel computing. And in a world of parallel computing, the computational complexity is not the only thing that matters. In fact, if you really want to get huge performance gain, it matters more if you can parallelize your processing into multiple different processor nodes, processors, or GPU nodes, or even like a cluster of machines. So that's why I'm saying, like, in this era, the computational complexity becomes less and less important as long as your problem is parallelizable. However, there are also problems that we identified they are hard to parallelize. Then if that's the case, then computational complexity is really important. So sometimes we say complexity doesn't matter. That applies to the problem that we can parallel them. We can parallelize them in massive parallelism. However, if it's not the case, we still need CS101. Now, before we start talking about our main topic today, try to correlate why inside out is related to the topic we are going to talk about today. I want you to discuss with a few friends of you and try to figure out what percentage of English words from the dictionary do you think you have to know for your everyday life? Okay, are you guys able to make a guess? How many English words, how many percentage of English words do you think you have to know? 8%? Okay, other guesses? 0.67? Why is that specific? You think it's a good number? Is it your lucky number of the day? Okay, what else? What do you think? 20%. How much? 1 or 2%? 15, 30%? 15 to 30%. Really? Okay. What else? 1%. Okay. So, but nobody would think we need 100%. Nobody would think we need to know half amount of the words, and we can still survive in the United States, everyday life without any problem, right? And sometimes, like for introverts like me, I typically, like if nobody was asking me out for a day, my conversation is probably just like, hey, oh, Pike Place, Grande, in a cup, please. Something like that. And then that's probably the only sentence I would say of a day, right? So depending on how you define everyday life. But there is a, a few, and it's very interesting in a way that sometimes we feel like we are living in a world that we are doing a lot of things for a rarely used case. This is not only just, and sometimes you will figure out that the resource of the world is not very well distributed. For example, like there are a lot of things about like 80-20 about like 80-20 laws in the world. So one of the things is that a lot of people would figure that out, right? Like the wealth of the world is pretty much like top 10% of person. They own like 67% of the wealth in the United States, and they don't have to pay a lot of taxes. That was unfair, right? So, yeah. Well, so one thing, if you find interest, well, if you're interested about me, like one of my side, like a half-time job that I would do is that I'm actually a text preparer for a lot of people, and sometimes like a lot of friends of mine, they are working really hard in companies, but like about like 33 to 40% of their salary are gone because of the tax. And they were asking me if there's any way they can avoid paying this. And unfortunately, what I would tell them is that because we are not that 10%. So the ways how we can avoid the taxes is actually not that much, which is very sad. But this is just one step. And the other thing is like, okay, if you are in software engineering, right, you will figure out that most of the time, people are just using 20% of the features or 20% of the code that you wrote. The other 80% of the code, they were there, but they are rarely used. So one of the things that people have been talking about with Microsoft Windows is that Windows has a very giant kernel comparing with other operating systems. And their code base is like thousands lines of code. And the main reason is not because they actually have to provide a lot of features in kernel. And in fact, the operating system kernel nowadays are not supposed to be really big because of the design philosophy. However, they have to maintain a large kernel because there are 80% of the time, people are going to use some legacy code that probably you're not using, I'm not using, but someone would use. Like somewhere in the world, there may be just only one person he would use, or she would use, or they would use. But you never know. And for that kind of perspective, you have to prepare for that. So like this is another rule of 80% of the users use only 25% of the features. And now regarding this, in fact, it's good enough for us to just understand 2,000 and 3,000 words in daily life, right? So that's about like 2% of the English word, and you can understand 90% of the conversations, right? So if someone said 2%, you had a very good estimation. But all that tells us is that most of the cases we are only using a small fraction of the vocabulary or the whole world's content. Right? So what does that mean to computer science? We will talk about that later. But today, we are going to talk about the memory wall problem, and we are going to talk about the predictable code behavior. We are going to talk about how are we going to design a hardware unit code cache that would capture this predictability. But before we start, we have to talk about what's the most critical problem in volume architecture nowadays. So as we learn from MDOS law, we always have to figure out what is the most common case and what's the most significant case. And by most significant, most common case is not the operation that occurs the most often. It's the operation that takes the most amount of time. And one of the things that we will mention is probably the memory access. So, so this graph, the horizontal axis is the year. And the year is plotted by the year a new memory standard has been published. And the vertical axis is the latency of accessing this new memory standard. And the blue line is the performance of CPU cycles based on the latency. And this green line is the DRAM access latency at different standard. And this pink line, or say the purple one, is the aspect ratio between this DRAM and CPU latency. Because at the end, you will figure out that CPU latency is really low. However, the DRAM latency, it does improve, but a very limited degree. So right now you can see the DRAM performance is probably 50 times slower than the processor. So so we have a huge gap between the processor performance and the memory performance. So is this really significant? So to understand, to get a feeling how significant is that, let's start by asking this problem. All right, let's take a look. Okay, so based on this, we have three answers that are very diverse. Well, not really diverse, but why don't you guys discuss with each other, try to convince another? Your answer is right. All right, so what do you guys think? Okay, so after the second round, more of you think the answer is B. Okay, so for this question, how should we start? To solve this question, what's the concept behind this question? What do we need to know to solve this problem? First of all, basic high school math. What's the second thing? No, not even performance formula. No. Well, that's something we have to know after that, right? But what's the big picture behind this question? What do you need to know to solve this question properly? First of all, high school math. Well, not even high school, elementary school math. What else? So a lot of you keep ignoring this, like keep coming to the classroom late because you think I'm reviewing things. But every time when I'm reviewing things, they are actually relevant. So what have we reviewed today? What are the slides that I showed up during the review part of the lecture? Volume architecture, okay. Mitchell, tell me more about what is volume architecture. Okay, we have memory, processor, storage. And then, how do we use them? How do we use them? Yeah, we have programs. Programs are instructions and data. And how do we execute an instruction? What's the first step of executing an instruction? Load it from the memory, right? You have to get instruction from the memory into the processor. So how much time that would take? How much time that would take to get an instruction from the memory to the processor? 13.75 nanoseconds, right? But we want to calculate the CPI, right? So everything has to be in cycle. So how many cycle is 1475 nanoseconds? 55, how did you know that? Right, so if you are having a 4 gigahertz processor, your cycle time is 0.25 nanoseconds, right? So divided by 0.25 nanoseconds, 55, right? Elementary school mathematics, right? So 55. And then, what are the rest? So now I get an instruction inside the processor. How many more cycles do I need to get this instruction processed? Where can you find that information? If the instruction is already fetched, how many cycles do I need to execute that instruction? One. Where did you find that? Right, right. So 1. Now, are we done? So there is a category of instruction called memory access instructions, right? So if they trigger an additional memory access, how many cycles would that be? If I need an additional memory cycles, how many cycles do I have to pay for that? If I need to access data memory again, how many cycles to access that? How many cycles? Yeah, right, 55. But am I going to access data memory all the time? What's the percentage, what's the probability that I'm going to access data memory? 20%, right? So what's the answer? Is there anything like require a high school degree here? 67, right? So a lot of you are trying to ask our TAs, trying to ask me if there is an equation for something. I want to say for this class, there is no equation is set for performance equation m-dot law, and later on there is one more. These are all the three that you need to know. And for this kind of problem, you just need to calm down. Think about what's the big picture. Every time I pull out a slide for phonemic architecture, it's not because I want to waste time. It's because it's really relevant to the rest of the discussion. So if I pull out that slide, that's a big picture. You have to remember. If you don't have the big picture, you are not able to solve this kind of problem. They are all based on big picture. And once you calm that down, once you figure out what's the process of executing an instruction in a processor, this is automatically something that you will figure out, right? So these are the problems that you have been solving very well since elementary school. Question?
Yeah, I just wanted to verify the calculation. So the first part is 55, and that's because that's to read an instruction in from memory. And then the 1 comes from processing the instruction. And then the 55 times 20% is because 20% are load or store instructions.
Yeah.
And that will cause us to read from memory again.
Right.
Or access memory.
Right. And that has been told many times since the very first lecture. Right? So, question?
Yeah, I have a question about the one CPI.
Uh-huh.
Is the one CPI to run the program?
What do you think? Already fetched an instruction, right?
And then, but is it 20% of the instructions in the program?
No.
That's separate.
We have say, right, if there's no memory access and the processor already fetched the instruction, right? This sentence is crystal clear. Question?
Yeah, so is one, like the one CPI is for 80% of the instructions, right?
What do you think?
Yes.
Yes.
So then why isn't it 1 times 0.8? Why is
Because for memory access instruction, you still have to experience this one.
Oh.
Right? Is that clear? So for this question, specifically, it's 67 cycles. And again, I don't know, like a lot of, from the last time I like having some remote office hour with people, I feel like a lot of us are trying to just find equations to apply to each individual problems. But listen, when you are taking any kind of system class, because the system, like computer system, like computer networks, computer architecture, operating systems, this kind of system class, there are so many components inside the system. If you try to find equation applied to the systems, you are going to fail. That's what I'm going to say. So if you are like, if you prioritize learning experience based on like memorizing equations, I really want you to abandon those in these classes. Otherwise, it's not good for you. Okay, But for this particular question, right, the reason why we got this answer is just because of that. And each of the term, it's not an equation. It's just because if you go through the volume architecture process, it's just because we need them in these processes, right? So we have 67 cycles. And for this 67 cycles, right, 66, except for that particular one, are related to memory. So what does that mean is that more than 98% of the time, you are spent in memory, right? You spent this percentage of time in the memory. Isn't that the most significant, right? So that's actually the most significant problem. And in fact, in a previous question, I put 20% as the data memory access instruction, but it's actually underestimating. If you check your textbook, you'll figure out that the data transfer instruction, they are actually around 35%. So what does that mean is that and also this is in fact the most important problem, the most critical problem in modern architectures. So the first takeaway is one memory operation is as expensive as 50 arithmetic operations, and a processor has to fetch instruction from the memory every instruction. And we have an average of like 33 or to 35% of data memory access instructions that we have to deal with. And because of that, memory is what really have to deal with. So that's why this class, after talking about how to evaluate the performance, after talking about in MDL we have to address the most common problem, we start with this most common problem, which is memory accesses. So some people will think, okay, if memory access is the main problem, let's use faster memory technology. And in fact, sure, if you have a limited amount of money to spend, why not? However, how expensive is that? So beyond DRAM, dynamic random access memory, which we use most commonly today, SRAM is the fastest and stable, mature memory technology. There are a lot of research on faster memory. However, SRAM is still by far the fastest. But if you look at the price, how much more expensive? Every bit is like 50 times more expensive. What does that mean is that today, well, and also like the majority part of your processor is actually built in SRAM. In memory cells today. So if I want to do that, what does that mean is that today I can buy a processor with $400, but times that amount of money by 50. That's what you have to pay for just one processor, even more expensive than an NVIDIA GPU. All right, so we are not going to do that. We are not going to pay for that. So the alternative solution that we have is that we make memory hierarchical. So we have nowadays, we know that we are going to accommodate really large but also fast, expensive memory in our computer system design. So we start to stack them as hierarchy. And we use the word hierarchy for a reason. So for hierarchy, it means that your processor only talks to its immediate level of the memory unit. So generally, when we talk about processor core, it includes the processor LUs and registers, because those are what the instruction directly interact with. And originally, our processor would interact with DRAM, dynamic random access memory, for data and instruction storage. However, because it is too slow, so nowadays we add another layer called SRAM cache, C-A-C-H-E, pronunciation exactly as C-A-S-H, right? Because, and an easy way to memorize it is that, cache, they are made with SRAM, so you have to pay a lot of cash for that. Okay, so SRAM cache. So when you see this dollar sign in our class, it doesn't mean you have to pay for it. Well, you really have to pay for it, but it means like cache. So what does that mean is that with the addition of SRAM cache inside your processor, the processor core assembly, which includes the processor LUs and functional units and registers, they only interact with the SRAM cache for the data. Only if the SRAM cache cannot accommodate my request, the SRAM cache would go to the lower memory hierarchy to search for other things. And for the lower memory hierarchy, it's typically like DRAM, which nowadays has gigabytes of storage and tens of nanoseconds to access. And if the DRAM doesn't have anything we want, we will go to the storage, which will cost tens of microseconds delay. And they would store data in terabyte scale. And typically in your SRAM, you can only accommodate kilobytes to megabytes of data because that's an affordable range of hardware resource that we can have. So let's correlate this to inside out. So if you pay attention to the movie clip, they mentioned the core memory. So the core memory are those the Riley's emotion directly operates on. So they are resembling the registers that we have in a processor. And there is a wall of this memory balls like behind their control centers. Those are the caches. So whenever they need to change Riley's emotion, they just fetch the stuff from the wall directly, which is really, really quick, right? If you remember what's that movie about. And on the same line, and if there are memories that are something that they cannot really find, they have to go to some short-term memory storage, which is located on the same island as the control center, right? However, if it's really, really long-term memory, right, they have to go to somewhere like a graveyard, which would take the whole movie long time to get it back, right? If you remember that movie, right? So that's pretty much similar to our memory hierarchy, is that the lower the memory hierarchy, the more you can store, but the longer time it would take to retrieve your stuff. So now let me ask you a second question. So how can memory hierarchy help in performance? All right, let's see. What do you guys think? Okay, I love this figure because it means that we really need some discussion. So why don't you guys go ahead and discuss with your friends regarding how you derive the answer that you like. All right, let's take a look regarding what you guys think. So now more of you think the answer is B. So apparently the discussion helps, right? So how do you get this answer? So now in between process and memory, we got L1 cache. How do you guys start with this? Right. Right. So this is actually, well, sorry. So this answer, no. This is actually this one. So I put it in the wrong place. So first of all, right, for the CPU cycle time, again, it's 0.25 nanosecond, right? And as that, yeah, right, as that said, right? So this, um, okay, so each cache access is now 0.5 nanoseconds, so it would take 2 cycles. And if we are unfortunate, we have to go to the DRAM, it would take 55 cycles, right? But are we that unfortunate most of the time? The answer is no, right? Because the chances that we need to go to the DRAM is only 1 minus 90%, right? So what does that mean? Is that each DRAM access, we only need this 55% for 10% of the cases when we access either instruction or memory. So all we need to do is to expand the previous calculation in a way that for the latency part, instead of putting everyone as 55, 90% of the time you only have to pay 2. 10% of the time you have to pay 2 plus 55. So some of you might be wondering why it's not 10% times 55, because without doing this, you are not able to know if I need to pay this 55. So I would say, right, so the disadvantage of this is that if you have to go all the way down to the memory, you are actually taking longer time than the past. That's hierarchy, right? Because you are strictly required to go through each part, and each part would incur new latency, right? So that's why I would say the word hierarchy is very important. Hierarchy is very important. The word hierarchy is very important in this context. So if you don't get a feeling regarding what is hierarchy, if you have ever been interning in a company, you know what is hierarchy, right? For example, say you work at Meta. Have you ever been able to meet Mark Zuckerberg directly? Or even though you work for Tesla, are you able to meet like that guy, right? A lot of us hate him, right? Elon Musk directly. The answer is no, because it's strictly hierarchical. If you want to meet the CEO, you have to go through your manager, your manager's manager, your manager's manager to approve. So it turns out the whole process would take several days or several weeks, even several months. If it's not hierarchical, you just send a message directly to your CEO, and then you can schedule an immediate meeting, right? So without hierarchy, from the bottom to the top is actually faster. With hierarchy, is actually slower. But why we want hierarchy? Because for the general case, it would help improving the performance. And that's exactly why the memory hierarchy looks like this. Question?
So just to reiterate, it's 2 plus because
You have to pay this 2 anyway.
yeah.
Yeah. Okay.
Wait, so in order to get to DRAM, you have to pay the L1 cache no matter what?
No matter what, right? Because without going to the L1 cache, you are not going to know if it's in the L1 cache, right? This is strict hierarchical, as I said. Your processor only interact with L1. Only if L1 cannot find anything, you will be forwarded to the DRAM, right? So without doing this, you won't be able to do this, right? Okay, so the answer is actually B, 10 cycles. Let me see what this is going to be about. Okay, so in fact, if you check the memory hierarchy that we have today, right? In your if you have a Windows machine, you can download a tool called CPU-Z, and it will show you your processor actually have a pretty complex memory hierarchy. It has L1 data, L1 instruction, level 2, level 3, right? And this is the same for Intel and AMD processor. And so in fact, the memory hierarchy is more complex in a way that this hierarchy itself also have multiple levels. There is L1, L2, L3. And again, similar to the memory hierarchy, the lower the memory hierarchy, your performance is actually, you will take longer time to access. And remember, it's not you can directly access L2 or L3. It's only if you go through L1, it's not found, we will go to L2, and then go to L3, and then go to the DRAM. So that's what a processor would look like. So now, why are we adding more hierarchies? All right, let's take a look. Okay, so, okay, why don't we just discuss with our friends and take a look of what you guys think afterwards.
Yeah, so it starts at level 1, that's 90%, and then 60% of that goes to level 2, and the rest goes to DDR. Right? Yeah, 60. So 90% is processed by humans, and then 10% go down. So I'm basically everybody generally plays yeah, this would be like
All right, let's take a look. So after the discussion, more of you think it's A. Well, it's only A and B now. So now let's take a look. So first of all, still, right? If this is the CPU cycle time, this is the L1 cache access time, and for L2 cache access time, and the DRAM access time. So what does that mean is that if we're lucky enough, we can find it in L2, L1. This memory access only need to take 2 cycles. And if we cannot find it, we have to pay 2 cycles plus 20 cycles. And if we cannot find it in L2, we have to pay 2 plus 20 plus 55. That's the whole story, right? And I just figured out that there is a inconsistency between the slides here and give me a second. Some of the stuff. Sometimes you have 2 stacks of slides. That's how you get stuff messed up. Okay, so this is the right one that I should be using. Okay, so for this one, right? So 90% of the time is satisfied in L1. So only 10% of time goes to the L2. And for the L2, it would go to 40% of the time you have to go to the DRAM, right? So turns out the average memory latency you have to pay is around 8.44 cycles, right? So it's closer to 10 still, but faster than 10. So what does that mean is that, right? What is that? So the answer is actually B, 10. But previously we are sharp on 10. Right now we are less than 10. So what does that mean is that we build more memory hierarchy because on average, it still helps. And fortunately, because we have more advanced process technology, so this can be built as cheaper. However, you also learn why right now we are satisfied with just 3 levels, not 4 levels or more levels. Because the more the levels we have, the smaller help we get from adding new memory hierarchy. So that's why the design only satisfied at 3 for now, because that's what we found to be optimal with the modern memory technologies. All right. So the second takeaway is that we build hierarchical caching with small amount of SRAMs will work if we can efficiently capture data and instructions. Now, the question you want to ask me is that if you pay attention to what my problem was saying about is, I am assuming the L1 can capture 90% of my data and instruction. Is that possible? So we want to talk about, in general case, your code and the data access pattern, they are very predictable. And sometimes if I show you some kind of code snippet, you probably won't have a feeling. So let's talk about machine learning. So the most use case of machine learning is actually inference. By inference, it means we take a model, trained model, we try to predict an instance, what category is that. So for example, like your day is probably with your starting with your Face ID, right? Whenever you are doing Face ID to recognize if that's you, you are doing the very first inference of the day, right? So what is so saying that, okay, Triton, right? He needs to recognize this is the iPhone of Triton. Then somewhere in your code, they have to perform a convolution plus ReLU, which try to extract some of the features from this whole image. And then to sharpen some of the features with min-max pooling, and then perform more layers of this feature extractions to extract as many features as possible as we need to recognize someone's face. And then the last layer is probably the most critical, called fully connected, which we try to extract those features as an array and multiply it with a trained model. And with that trained model, you are going to get a vector with probability regarding how likely this instance belongs to. And if we recognize there is a high chance it's going to be Triton, then we can 100% for sure that's Triton. Otherwise, if the confidence level is too low, we will probably reject and ask the user to try again. And this fully connected is basically perform a vector matrix multiplication. So for this vector matrix multiplication, you would typically write a C code like this to perform vector matrix multiplication. So regarding this, based on the readings that you have made before this lecture, can you tell us what kind of locality do we have? All right, let's take a look. Okay, so why don't we discuss with friends and see if we can reach a consensus later.
But maybe if it's like lower quality and matrix J will access different elements of vector G where it's much as the same size as access the I, and then I think that's
I guess more of
Yeah, because matrix is really technically you do come back with factors, but every time you actually use that, so access actually it does because access
All right, let's take a look. Okay, after discussion, more of you think it's E. So what is E? Both matrix and vector have spatial locality. Vector also has temporal locality. So what is spatial locality?
spatial locality is that like when you're accessing memory address, you can access a nearby memory
Mm-hmm.
address in the future.
Mm-hmm.
It makes it easier for the program to access the location quickly rather than needing to jump around.
Right. So spatial locality means that your program code has a pattern where you would access neighboring items, right? So do we see that in matrix or vector? Right. So if for matrix, right, if I am visiting I and J, what's the next? I plus 1? J plus 1, right? And if we order this matrix based on rows, like we put each row in neighboring items, this is actually spatial locality because I'm accessing the next. How about vector? When I access J, what's the next? J plus 1, so that's spatial locality. So what is temporal locality?
It's like when you access the same memory location over and over again.
Yeah, access memory location over and over again, right? So where do we see that? Are we going to access the same matrix IJ again? Why not? Because the I changes, J changes all the time, right? So how about this vector? Are we accessing the same element again and again? Right? Although the IJ changes all the time, but when I changes, I would go to the same J again, right? So I would access the same element again, and this doesn't exist. And for output I, we'd also have spatial locality, but no temporal locality, right? Because we only access it once, right? So the thing is that, well, like as we said, output has spatial locality, spatial locality, spatial plus temporal locality. So what does that mean is that your code is very predictable, right? We know if you access I, you are going to access I plus 1. If you access J, you are going to access J plus 1. That's spatial locality, right? So for example, like, okay, one of the success formula in shopping mall is that they have to find the most attractive stores, right? So as long as you find one shop that you like, you will go to that place often. That's called temporal locality. And if you already went to that place, you are trying to find neighboring shops if you have other like desire you want to satisfy. So for example, like UTC, right? I typically go to UTC for like boba tea, right? It's probably easy for you to guess which one, but they don't pay any money, so don't want to advertise for them. But because I'm already at UTCs, then I would know if I want to purchase like clothing, then I would try to find other shop in UTC rather than go somewhere really far away, right? So your cache pretty much, and that's our human behavior, right? And your code also have that behavior. So a quick demo to show you this is that, oops, not found. What happened? Okay, not found. Why? Really? Okay. What? Sanji. What's your favorite? Okay. Well, he's not normal. So I like those characters who are like normal human beings, but with more capability. Anyway, okay, so let's take a quick look of this demo. So saying that, I have a matrix vector code like this, and now let me compile it. Oops, that's actually not the demo I want to show. Okay, this is the demo I want to show. So let's say this is my program, which is the matrix vector. And in this matrix vector, I try to dump, I try to dump the memory addresses that I access for each this operation by printing out the matrix and the vector value. And let's see what their address look like. So with this one, you will see, because our program, when we load it into the operating system, we would do something like a shuffle. So when you load your dynamic data, we start with a different stack for safety's perspective. But if you dump this address, you will figure out that, okay, we start by accessing A00, which its address is blah, blah, 330. Remember this 330. And now for B, which is the vector, it ends with like AC30, right? Remember this A330. And now when we go to 01, it's the prefix, they are pretty much the same. And then A338. And this 8 is only 8 bytes away from the previous address. And why is that? Because we are accessing double. So the address is 8 away. And for B, right, the same thing, right? It's C30, but now 38, right? So it's also 8 away. So your address is very predictable. And now, if I change to be a column access, which means that instead of doing I and J, I'm doing it with J and I. What's going to happen? So this one, okay. So if I do it in a different order, like J and I, then this is what I'm going to see. So first of all, I'm still starting with the same address, but let's see. The next address, instead of going to 3A, it's going to C0 for matrix. It's far away, right? So in this way, you can imagine like, okay, I'm now at UTC, but the next stop is like Carlsbad, for example, right? And then go back to UTC again, right? This kind of a route is definitely not an optimized for memory access. So that's why when you change the loop order, your performance gets really bad because your code becomes not really very predictable, which is hard for our cache to have. So the thing is that you want to make a hardware unit being able to predict what's going on, right? And in fact, if you check the memory layout in our memory, it's pretty much like this. You have a section of code, you have a section of memory structure, and the same memory structure, it would lay out based on the role. So if you can go with this order, or you can reuse this small section again and again, your code performance can be really good. On the other hand, if I can build a hardware unit that can capture these small pieces successfully, then I can also make the code performance very good. And from the code perspective, we just talk about, so far we just talk about the data access part. How about the code? And in fact, your code has even stronger locality. So this is the compiled version of the code. So a lot of us like to write for loop, but there is never for loop in assembly language from the compiler's perspective. For the compiler to compile the for loop, they would typically translate it to a while loop. And for this while loop, you can consider the next statement. They are spatially next to the previous. So when you execute your code, first of all, you will going forth through. So after you finish this statement, you are likely to execute the next statement, that spatial locality. And we love loop. So whenever you have loop, you are going to revisit the same set of instructions again and again. So the code itself also has very strong locality. Make your behavior really easy to capture. So in fact, the rule of locality tells us that your application is actually very predictable, even though you are visiting a large amount of data. However, within a very small period of time, you are only going to use a very small amount of data and instruction. So that made it possible for us to create some kind of hardware to exploit this kind of locality in our code. So to follow that, right? So if we have a spatial locality, it means that if we find out that the processor, or say your code, is accessing something that we have never seen before, instead of just getting that specific instance that the processor is asking for, I should get a bunch of them together at the same time. And based on the rules of locality, they should be the stuff spatially nearby each other, right? So the first thing is that we need to cache consecutive memory locations every time when we have a cache miss. So that abstraction is called a block. And then, so what does that mean is that, okay, now if I have an instruction like this move, I found it's a miss. Instead of just getting this vector, which the next time when I access a new vector, I still have to fetch it from the memory, which causes no benefit. I should do this. Every time when I have this instruction missed, I should fetch the whole block of stuff, which contains not only the vector 0, but also all the vectors that are next to each other together into the cache. So that next time when I need to access this vector 1, it's already in the cache. So that's the very first rule, the first high-level design decision we have to make in designing the cache is that it's always block in, block out inside the cache. Every time when there is a cache miss, it's always in a granularity of a block. That's the first rule. Now, the second rule is, okay, my cache has to store more than one block. Why is that? Just look at this. If I can only have one block, I can only cache one data structure. However, most of the time, within a very small window, I'm going to access multiple data structures at the same time. So I need to have multiple blocks, right? So the rule is that I have to put multiple blocks of data inside my cache. And again, when I have a miss, I am fetching a block, whole block inside the cache. Right. So that's that still holds, right? But the difference is right now, your cache needs to have multiple blocks available to store, right? So that's the idea of cache. You need to cache multiple frequently used memory blocks. And the cache must be able to distinguish blocks because right now we have multiple blocks, we have to distinguish them. So the next lecture, we will talk about how to distinguish them. But before we leave the classroom, I think we have to talk a little bit. So I found there are a lot of people missing reading quizzes. I don't know why, but it's always on Gradescope. So just make sure that you check the Gradescope open. And we have trying our best to tell you guys when it is due, right? And we never change the due date. So you should have a very good track about when are we going to have those reading quizzes due. The next one is going to do this Wednesday. I'm going to put this up later tonight, so you can start working on it. Assignment 2 is already up, and again, our assignment is very customized, so everyone would get a very different performance measurement, so no one should have the same. And as I mentioned many times, don't round your number, just copy paste your measurement, put those in your equation. And the last time we have a very relaxed checker for that because it's the first time. But this time, just make sure that you have to get the correct estimations as detailed as possible. So it's already up, but based on the content we have taught today, it's probably too early for you to start, but doesn't hurt to get a look of that. Other than that, enjoy the rest of the day. I will see you tomorrow.